Hi, my name is Anjani Rana, and this is my black hole lab. To introduce the lab, we'll be trying to determine the unknown mass of a black hole by looking at the motion of a star as it orbits the black hole. We will be using two fundamental principles throughout this lab, the momentum principle and the law of universal gravitation. We will see evidence of both these principles as we look at the Python code used to create a computational model of the star orbiting the black hole. We are interested in this lab because it allows us to use data regarding the motion of an object in order to calculate an unknown variable such as mass. The use of these principles in this form of iterative calculation can also be applied to find other unknown variables such as radius. To begin, we'll look at the while loop of our Python code and how we applied fundamental physics principles in order to develop a working computational model. First, we'll look at how the momentum principle helped us define momentum, net force, and dp/dt. As we know, change in momentum is equal to F net times change in time, where momentum is equal to mass times velocity. We first define momentum as indicated here, where P initial is equal to star m times V initial, and P final is equal to star m times V final. We then must calculate dp/dt. We can arrange the momentum principle such that F net is equal to change in momentum over change in time, and we make the assumption that the value of delta t is small enough so that delta t over delta p is equal to dp/dt. Therefore, F net is equal to dp/dt. Here we can see where we define dp/dt as delta p over delta t, and here we can see that we define F net as dp/dt. In this next slide, we can see how we continue to use the momentum principle as we break down each term into their individual components. As we know, F net can be broken down into both parallel and perpendicular components. Based on the momentum principle, F net is equal to dp/dt. We define this in our while loop here. Therefore, the parallel and perpendicular components of F net are equal in value to the parallel and perpendicular components of dp/dt. The sum of dp/dt parallel and dp/dt perpendicular equal dp/dt. We use this statement to redefine dp/dt perp as dp/dt minus dp/dt parallel. This can only be done after we define what dp/dt parallel is equal to, which is the change in the magnitude of momentum over the change in times p hat. The last thing we must do in our while loop is use the law of universal gravitation in order to find the mass of the black hole. According to this law, the magnitude of net force is equal to the gravity constant times the mass of the star times the mass of the black hole, all divided by the magnitude of the relative position of the star squared. We then rearrange this so that we're solving for the mass of the black hole, such that MBH is equal to the magnitude of the net force times the magnitude of the star position squared, all divided by this gravity constant times the mass of the star. After running the code, and watching it orbit the black hole, as shown here, the mass of the black hole was found to be 1.64849 times 10 to the 34th power. The magnitude of the net force acting on the star at its final position was found to be 9.54931 times 10 to the 28th power. To answer the what does it mean question of what is the difference between F net and dp/dt and their components, F net and dp/dt and each of their components are equal in value, again assuming the change in time is small, according to Newton's second law, which, when rearranged, states that F net is equal to the change in momentum over change in time. However, the meaning of these two differ, in that F net refers to the amount of force acting on the system by its surroundings, whereas dp/dt refers to the rate at which the momentum of an object changes in time. So therefore, dp/dt refers to the change in motion of an object, and force refers to the amount of force acting on the object. To answer our what if question, which asks what would happen if our current black hole was removed and replaced with a different black hole. If the motion, position, and mass of the star remains unchanged, this would mean that the force acting on the objects would remain the same based on the momentum principle, as we can see here. We will use this force in the law of universal gravitation because the only force acting on the object is the force of gravity. And because the gravitational constant, mass, and relative position of the star do not change, then the mass of the black hole will remain the same. Thank you.